Hello, welcome to Digital URIM. In the previous video, we studied SGID and sticky bit, two special permissions that are important for understanding how Linux handles groups, shared directories, and file protection in multi-user environments. We learned something important. A special permission is not bad by itself. The risk appears when it is misconfigured, poorly documented, or applied in the wrong place. Today, we are taking the next step. We are going to study processes, services, and scheduled tasks in Linux. Because as a cybersecurity analyst, it is not enough to know what files exist on the system. You also need to know what is running, who is running it, and with what privileges. A process is a running program. For example, when you open a terminal, run a command, or a service starts in the background, Linux creates a process. A file like /usr/bin/ssh may exist on disk, but when it runs, it becomes an active process in memory. This difference matters. A file can be stored and do nothing, but a process is alive. It is using CPU, memory, permissions, network connections, or system resources. From a cybersecurity perspective, a process can be a legitimate application, a system service, an administrative script, a scheduled task, a misconfigured process, or suspicious activity. That is why an analyst must know how to observe processes. A basic command to view processes is psaux. This command shows active processes, the user running them, CPU usage, memory usage, and the associated command. But we should not read the output as just a list. We should ask questions. Which user is running this process? Why is it running? Is it normal for this server? Is it consuming too many resources? Is it running as root? Does the command look legitimate or strange? In Linux, every process runs under an identity. It may run as a normal user, a service account, or root. This is critical. A process running as a low-privileged user usually has less impact if something goes wrong, but a process running as root has very high privileges. Root can modify system files, change configurations, install software, read sensitive information, and affect the entire system. That is why, when an analyst reviews processes, one of the first questions should be, which processes are running as root? We can use ps-eo PID user group com args --sort equals user. This command helps us see the PID, user, group, command, and arguments. The PID is the process identifier. For example, if we see a process with PID 1234, we can investigate more information about it. We can review details with ps-p 1234-opid PPID user group com args. The PPID is the parent process ID. This helps us understand where a process came from. For example, if a process was started by systemd, it is probably a service. If it was started from a user terminal, it may be a manual execution. If it was started by cron, it may be a scheduled task. That relationship matters during investigation. A common beginner mistake is thinking, if I do not recognize the process, then it must be malware. That is not correct. Linux has many legitimate processes that may look strange if you do not know them yet. The analyst's job is not to assume. The analyst's job is to verify. A process may be suspicious if it runs from an unusual location, such as /tmp. It runs as root without a clear reason. It uses a name similar to a legitimate process. It consumes many resources without explanation. It restarts automatically after being killed. It is associated with unknown network connections. It is not documented on the server. For example, it is not the same to see /usr/sbin/sshd as seeing something like /tmp/sshd. The first one may be the legitimate SSH service. The second one requires immediate investigation, because TMP should not be the normal location for a critical service binary. This is an example of a detection signal. We are not automatically saying it is malicious, we are saying it deserves review. A service is a process designed to run in the background and provide a system function. For example, SSH allows remote access. Apache or Nginx serve web pages. Cron runs scheduled tasks. Docker manages containers. Firewall-D or UFW help with firewall rules. In many modern distributions, services are managed by systemd. We can view active services with systemctl list-units --type equals service --state equals running. This command shows services running on the system. From a security perspective, this is very important. Every active service may represent attack surface. If a server does not need a service, that service may increase unnecessary risk. For example, an internal server that does not require remote access should not have SSH exposed without control. A server that is not a web server should not have Apache or Nginx running without a reason. An old or misconfigured service may open a door for attacks. The analyst's question is, should this service be active on this system? Not every active service is dangerous, but every active service should have a reason. If we want to review a specific service, we can use systemctl status SSH, or depending on the distribution, systemctl status SSHD. This command can show whether the service is active, how long it has been running, the main process, recent messages, whether there were errors, which systemd unit manages it. We can also review logs with journalctl-u ssh --since 1 hour ago, or journalctl-u sshd --since 1 hour ago. This helps answer questions like, did the service fail recently? Did it restart many times? Are there connection attempts? Are there authentication errors? Is there activity outside normal hours? In a systemd environment, logs are essential. A process tells you what is running. A service tells you which function is active. Logs help you understand what has been happening. A scheduled task is an instruction configured to run automatically at a specific time indefinitely. In Linux, a common way to do this is with cron. For example, a task may run every minute, every hour, every day, every week, at system reboot. Scheduled tasks are very useful for administration. They are used for backups, updates, file cleanup, reports, internal scripts, and maintenance. But from a cybersecurity perspective, they are also important because they can be used for persistence. Persistence means something is able to run again even after the system reboots or the initial process ends. That is why an analyst must review scheduled tasks. To view the current user's tasks, crontab-L. To view system-scheduled tasks, we can check locations like ls-lah/etsy/cron.d, ls-lah/etsy/cron.daily, ls-lah/etsy/cron.hourly, ls-lah/etsy/cron.weekly. There are also systemd timers, which work like modern scheduled tasks. Systemctl list-timers. The analyst's question is, what runs automatically and with what permissions? One of the most important risks appears when a scheduled task runs as root. This is not always bad. Many legitimate system tasks require high privileges. But if a script executed by root is poorly protected, the risk can be serious. For example, imagine a scheduled task running this script, /usr/local/bin/backup.sh. If that script can be modified by an unauthorized user, then that user may be able to change what root executes automatically. That is a real operational risk. The problem is not only cron. The problem is the combination of automatic execution, high privileges, a file writable by the wrong users, lack of monitoring, lack of documentation. Here we see how previous topics connect. File permissions matter. Users and groups matter. Processes matter. Scheduled tasks matter. Everything is connected. When reviewing processes, services, and scheduled tasks, do not think only about commands. Think about questions. For processes, what is running? Who is running it? Where is it running from? How long has it been active? Is it using abnormal resources? For services, which services are active? Should they be active? Are they documented? Do they expose network access? Do their logs show errors or suspicious activity? For scheduled tasks, what runs automatically? Who runs it? With what privileges? Is the script secure? Can another user modify it? This way of thinking separates someone who only uses Linux from someone who analyzes Linux from a cybersecurity perspective. Imagine you are reviewing a server and you run ps aux. You see a process running as root with a strange name. Then you review services. Systemctl list-units --type equals service --state equals running. You do not find that process as a documented service. Then you review scheduled tasks. cron-tab-l ls-lah/etc/cron.d systemctl list-timers. You find a task that runs a script from /tmp. That is an alert signal. Why? Because /tmp is a temporary directory. It is not a trusted place for permanent administrative scripts. Also, if the script runs as root, the impact may be high. The analyst's decision is not to panic. The correct decision is to document the finding, verify the file owner, review permissions, review the script content in an authorized environment, review logs, confirm whether there is an administrative justification, escalate if it is not documented. This is professional analysis. Today you learned that in Linux, files and permissions are not the only things that matter. What is alive on the system also matters. Processes, services, scheduled tasks, users running processes, associated privileges, automatic activity. As an analyst, your responsibility is not to memorize every process on the system. Your responsibility is to investigate, ask good questions, and recognize risk signals. In the next video, we will go deeper into a very important area: Linux system logs. We will study what logs are, where they are stored, how to read them, how to use journalctl, how to review authentication events, how to connect processes, services, and logs during an investigation. Because if processes tell you what is running, logs help you understand what happened. Understand, defend yourself, grow.